Hello and welcome back to my favorite people. It's good to see you again, and thank you for watching this video. And before I start this video, I want you to put a nice smile on that face because I want you to at least start your day with one accomplishment, and that accomplishment is gonna be changing your mood. So let's have a nice smile on that face. If you do military service early in the morning, sometime around 4 or 5 a.m., somebody will get to technically to the dorm and will ask you to wake up, and by the time he gets back to the end of that dorm and get back to you, you need to have a proper clothes in the front of proper clothes, and also your bed must be completely made and is really good shape. And what's the reason behind it? Why do they care that a lot about your bed? Because they want to give you this technically thought that you started your day with one accomplishment, and that accomplishment was making the bed. So have a nice smile and that face, and let's go after it. Okay, we're going to talk about carbon-cation, and here we have a positive charge sitting on a carbon, and that carbon is attached to three carbons. So I'm going to call it tertiary carbocation. And the second one, it has only two carbon attached to it, and one of them was replaced by hydrogen. So let's highlight the hydrogen. And that's going to be a secondary carbocation. Next, we have two hydrogens and only one carbon. So that carbon is going to be a primary carbon. And the last one, as you see, I replaced all the carbons with hydrogen. So that's going to be a methyl, technically a methyl carbocation. Now, when it comes to stability, we say the more atoms are involved, to accommodate that positive or negative charge. We say the ratio of the charge over volume goes down, so the system will be more stable. And remember this, that group like alkyl groups are electron donating group. Okay, so they donate electron. The more we have from them, the higher higher actually putting electron in or giving electron to the carbocation, a higher ratio. So how about this? I'm going to say I have more carbons neighbor with the carbon with a positive charge, so they will donate more. And now that donate more, that carbon, it will be more stable. Okay, more stable. So the order for them is going to be this. Okay, and in fact, last two, it's going to be so hard really to see them or catch them. And for sure, the last one, we're not going to see it, but the primary is not going to be stable at all. And so it will try to turn to either the secondary or tertiary if it's possible. Okay. And for example, in this case, we have a primary carbon, a primary carbocation, and that primary carbocation is neighbor to a carbon that it has two carbons and one hydrogen. Now, is there any way to turn a primary carbocation to a tertiary carbocation by, for example, moving a hydride or methyl group? Let's give it a try. And so if we take this carbocation and switch position of this hydrogen. So this hydrogen technically is a hydride. It has two electrons. I'm going to move this one and I will put it there. In that case, I will have the hydride here attached to this carbon, and that one, because it's moved with the two electrons, now is going to give me a positive charge. I have a positive charge on the carbon that is attached to three carbons, so this one turned to a tertiary. How did I get it? I moved a hydride, okay? Hydride, H with a negative charge. Now, what if it's methyl? Okay, if the neighbor is methyl instead of hydrogen, and what will happen in that case? In that case, you're going to move entire of the methyl, okay? Entire of the methyl. So this one will move with negative charge, and you will get this. Okay, so this one, it will be gone. Okay, the methyl, it will be gone. We will have a positive charge there, but the methyl, it will show up here. Okay, and again, we got a tertiary carbocation, and tertiary carbocation is more stable. So if it's possible to turn a primary carbocation to tertiary by moving hydride or methyl group with, like, it's going to be methide, that means with a negative charge. And if it's possible to move it and get a tertiary carbocation, then do it. Okay, this molecule will do it. Why? Because you make the carbocation more stable. Okay, now what do we have here? So the previous case, we had primary carbocation. There was a positive charge on it, and in this case, I have a secondary. Okay, secondary carbocation, and the secondary carbocation attached to the tertiary carbon. Okay, again, you can just simply move the hydrogen, and if you move hydrogen, so let's copy paste this one. Okay, so if I move the hydride, that hydride is gone. Now I'm going to put the hydride here. Okay, and that's going to leave me with a positive charge on carbon, and this carbon now is going to turn to, okay, this carbon is going to turn to tertiary. I need to adjust those. I don't know why it did not copy paste them. Okay, so here we have a carbon. And so I managed to turn secondary carbocation to a tertiary carbocation. How? By moving one hydride, and this is gonna happen. Again, you can repeat this one by moving this time methide group instead of hydrogen group. So in this case, we're going to move the CH3 with -1 charge, and the CH3, we're going to put it here, CH3. And where was the CH3? It used to be here, so that one is gone. Now I got a carbocation, and that carbocation is a tertiary. So from secondary, I turn it to tertiary by moving a methide group. The first one was through hydride transfer. Okay, again, I want to remind you that you can only do this rearrangement if the methyl, or say the hydride, is one bond, only one bond far from the carbocation. And if you look to them, okay, those two carbons are neighbor, attached to each other. Okay, and so the one that we moved it is here. Okay. And so it's sitting on carbon, tertiary carbon, that's attached straight to the carbocation. So there is only one bond between them. Again, this is one bond, and this is the methyl group. So you cannot move any hydride or methyl if there are 2 or 3 bonds far from the carbocation. 2 or 3 bonds. I'm not including this one in my calculation. Okay, and simply I say, where is the carbocation? Okay, and where is the substituent? The substituent is sitting on this carbon. And again, this is the substituent. I'm moving it. How far is it from the carbocation? Just one bond. Okay, and okay, now I want to talk about SN1 and E1. And what's SN1 or E1? So if it's possible, okay, if it's possible to create a carbocation and during a nucleophilic substitution, and the mechanism will go through that direction. Okay, why? Because again, activation energy is going to be lower. If the activation is lower, a reaction will prefer that direction. Now, the first step of the reaction is going to be losing the leaving group. When you lose the leaving group, you will get a carbocation. Now, what will happen to that carbocation? There are 2 scenarios. One of them, the carbocation will be attached to a nucleophile. A nucleophile will attack it, and it will give you a nucleophilic substitution. Or when you get that intermediate, or the carbocation, that intermediate or carbocation, it will maybe go through elimination, and you will get alkene. So we're going to have 2 products. One, nucleophilic substitution, and the second is going to be elimination product. And the mechanism will only be subject to concentration of the substrate. And why only this substrate? Because the rate determining step, it will be the taking nucleophile, taking the leaving group out of the substrate, or breaking the bond between nucleophile and the substrate, the substrate or the starting compound. And so this is going to be the rate determining step. And so you need to know the activation energy for it. The activation energy for this step is going to be the highest one. Now, after you get the carbocation, the reaction is going to be fast, and the reaction might go through 1 or 2 steps. It doesn't matter really how many steps from now it will go to get the product. And the only thing I care about it, first step is the slowest one. Okay, so this one is slow, and it will be the rate determining step. And again, here I have 2 steps. So this is going to be EA2, and that one it will be EA3. I have 3 steps, and rate of reaction only and only is going to be subject to the first step. And question, what do I have inside the first step? The only thing I have is a substrate that is losing leaving group. So I'm going to say rate is going to be rate of the reaction, or the rate law is going to be equal to K multiply concentration, and concentration of the, for example, the alkyl halide. Okay. Alkyl halide. And how many of them? Just one. So I'm going to say this one, it will be to the first. Okay. And if your solvent is involved in this chemical reaction, and solvent is the reason that living group is leaving the system, in that case we say this is solvolysis. Solvolysis, that means the driving force for taking bromide, for example, from the system is the solvent. Solvent can behave as a nucleophile, and the solvent is the reason that we are losing the halide. We will go through this one in next videos, but for now, I'm going to stop here, and thank you very much.